So with all these addition reactions, there's one more thing that we have to consider. Not only do we have to think about Markovnikov's rule or anti-Markovnikov or whatever, what have you, right? We have to think about where is the conjugate base going to attach. We also have to think about what is the stereochemistry, because addition reactions are a great way to create sp3 carbons that have a bunch of different things attached to them. And so we're going to be creating some stereocenters. So we have to think about stereochemistry when we do some of these, not all of them, but some of these addition reactions. So hydroboration is really the first one where we come across this, right? And we're going to talk about Syn addition and what that means, right? So if we take an example of a hydroboration, right, we have this thing here. So this has a carbon-carbon double bond where we connect a secondary carbon to a tertiary carbon. We're going to use BH3THF, hydrogen peroxide, and sodium hydroxide. And what we'll get out is, of course, the anti-Markovnikov product, where the hydrogen ends up attached to the more substituted position, and the oxygen ends up attached to the less substituted position. And now we notice that we have created two new stereocenters. And so naturally we want to know, are we going to make enantiomers? Are we going to make diastereomers? Are we going to make one diastereomer but not the other? Are we going to make one enantiomer and not the other? Right? And it turns out that what we're going to create is we're going to create a single diastereomer as a pair of enantiomers. Right? So the relationship between these two stereocenters is going to be the same. They will either be SS or RS, right? They'll either have the same orientation or they'll have different orientations, but they will be a pair of enantiomers. So you could have SS and the RR compound, or you could have the RS with the SR compound, depending on how this goes. Furthermore, we can predict, right? We can predict which one, and the answer is that the new bonds formed, right? In this case, the CH and the CO bond, right, will have the same orientation. Right? So when we draw this, that means that I'm going to make this hydrogen come forward. That means that the OH will also come forwards. They'll both be wedged bonds, right? You could also draw both of them dashed, right? That would be the enantiomer. So like I said, we'll get a single diastereomer, but it will be a pair of enantiomers. So if you draw them both forward, if you're looking at an answer key and I drew everything with wedges and you drew everything with dashes, you've just made the enantiomer, and that's perfectly fine, right? So two new stereocenters, the new bonds are formed in the same orientation. We call this orientation Syn. So we're doing a Syn addition of the hydrogen and the OH across the double bond. Okay. So in hydroboration, the reason for this is because when we do this concerted process where these two things in here, we had talked before about how this is a really organized transition state. They have to be lined up exactly the right way. The boron has to be over here. The hydrogen has to be back here, right? All of those things. And that carries over into the stereochemistry as well. In order for this to work, the alkene, this is the alkene and this is the borane, right? They have to be lined up so that the borane comes from only one side. We can't add it going across the double bond like this, where the boron adds from the front side and the hydrogen adds from the back side. That's not how bonds break. So instead, they add like this, where both the boron and the hydrogen add from the back side, right? So in this case, they would both be dashed. Or the borane can come from the front side, and in this case, both the boron, or both the hydrogen on this side and the boron on this side would both be wedged. right? But they have to be the same. They either both have to be wedged or they both have to be dashed. And that's what we see. That's what we call Syn addition. All right, so now you're worried, oh man, all those other reactions that we learned, was there Syn addition going on there? The answer is no. Any mechanism with a cation does not form a single diastereomer, right? So, right, anytime we have a cation, so oxymercuration, HCl, HBr, HI, H2SO4, any of those reactions where a carbocation is in the mechanism, we do not worry about stereochemistry because we can't predict what the stereochemistry will be, right? It doesn't form a single diastereomer. Instead, we get a mixture of all possibilities, right? So if you have a carbocation reaction, right, HCl, HBr, H2SO4, oxymercuration, any of those, you don't have to draw in wedges and dashes because we don't know what they will be. And kind of no matter what you draw, that's a possibility because we don't know, right? If you get the hydrogen and the oxygen are going to end up facing the same way, the hydrogen and the bromine might end up be opposite each other, or they might be the same. We don't know. You'll probably get a mixture of both. So in those cases, you just don't have to worry about it. Right? But in hydroboration, we do because we only get one possibility. They have to be the same orientation. They have to be syn to each other, right? So we'll do a couple more examples. The next couple examples you're going to see are actually also Syn additions. So we're going to do a couple examples like that. And then we'll do an example where we get the opposite thing, where the new bonds are always formed opposite each other. So one is forward and one is back, or one is back and one is forward. So we'll talk a little bit more about stereochemistry as we go through these other reactions. And then well, you'll get some practice to kind of nail all of this down. And hopefully all of this will make sense. This is one of those things, like I said, the list of reactions is getting pretty long, right? We've already got a lot and there's more coming. So please, please, please make your list of reactions. Keep adding to it, keep filling in all the details. Now we've got stereochemistry that we have to add on to these, right? We don't have to worry about stereochemistry for oxymercuration or any of the strong acid additions, but hydroboration we do. The next few of the reactions that you're going to see in the next videos, you're going to have to worry about stereochemistry. So add that column to your list so that you can keep that in there. And under hydroboration, put down Syn addition. Okay, so see you in the next one. We'll do some more Syn additions. You'll see that they are pretty similar to what we just talked about. See you there.